Да, значит, следующий докладчик Юрий Аркадьевич Кордюков. Вот, он расскажет об исчислении главных символов контактных многообразий. Слова знакомы. Я сочетал.
Okay, so let me send the analysis for the invitation. Okay, this is the title of my talk, the principal simple calculus on contact manifolds. And actually, I will describe two settings. So I first consider just compact Riemannian manifolds and elliptic series or series of elliptic operators. And then I pass to compact sub-Riemannian contact manifolds and related hyperelliptic operators. And I will address two questions. First, this is pseudo-differential calculus and C-star algebraic approach to pseudo-differential calculus. And second, so-called the trace theorem. And let me just start with the standard theory. So I remind, so suppose X is a smooth compact manifold of dimension D. And you see here just the standard form of pseudo-differential operator. And I will only consider the so-called classical or polyhomogeneous pseudo-differential operators, which means that the complete symbol of this operator is represented as an asymptotic sum of homogeneous functions. And it is well known that in this case, the principal symbol of this pseudo-differential operator locally is just top degree component, so just M, so homogeneous of degree M. And locally, this is a function on the cotangent bundle of the manifold, which is homogeneous of degree M with respect to natural action of multiplication group by reals in fibers of cotangent bundle. And we have a principal simple mapping, just a star homomorphism of these algebras. And on the right-hand side, so the codomain of this principal symbol mapping is just functions. We may say here, let's consider zero-order pseudo-differential operators. Then we may say that the principal symbol is homogeneous of degree 0, which means just constant along this orbits of this section, or we can say that this is a function on the cosphere bundle. And sometimes it's more convenient to talk about homogeneous functions on the tangent bundle. And well, it is well known, and we know that pseudo-differential operators invented in the 60s were useful in two, maybe there were two motivations for this. First, this is elliptic theory, so elliptic regularity and parametric construction. And second was index theory. And I will talk more about index theory. And index theory, first of all, this means that this was a possibility to make deformation. So if we deform the symbol of even, we consider differential operator and deform differential operators, we go out of differential operators. And we have a deformation between two differential operators. So this deformation goes through this pseudo-differential operator. And also properties like homotopy invariance of symbol appeals to continuity properties. And for these purposes, it's natural. So first, I will talk now about zero-order differential operator, pseudo-differential operators. Then we know that this is a bounded each operator is a bounded operator in L2 space. And we may consider uniform closure of the algebra of zero-order pseudodifferential operator. Then all these asymptotic expansions are lost, except for the leading term. And so then the closure will be what is called cyst algebra, uniformly closed algebra of bounded operators. And it turns out that the principal symbol map extends to this subjective. So this is a sub-homomorphism. Now we have the principal symbol map just as a continuous function, which is subjective, and the kernel just the compact operators. So the operator is compact if and only if the principal symbol is zero. And we can formulate this property saying that we have a short exact sequence. And this is a famous sequence in short exact sequence in pseudodifferential calculus. And this sequence first appeared in the initial paper by IKEA Isinger on index theorem, and it plays an important role there. So once we have such a short exact sequence, we can consider associated sequence in game theory and so on. And actually, this is a way to define the index. And on the other hand, it is essentially equivalent to this fact. So if we take any operator from this closure of pseudodifferential operators, and if we will try to approximate these operators by compact operators, so the best approximation is given just by the norm of the symbol. And this equality, this result was proved for singular integral operators before pseudodifferential operators by Goldberg and Seeley. And sometimes in this context, this statement is called the Goldberg lemma. And so first, so this is the first purpose of our first paper with, I forgot to say, this is a joint work with Fedor Sukachev and Dmitry Zanin from Australia, from University of New South Wales. And we developed a cyst algebraic approach to, so this is, if you will, the P Journal for Non-Primitive Geometry. And we developed another approach, so not going through this, another approach to this calculus of pseudodifferential operators, not with closures, so like a cyst algebra, and to this principal symbol map, which is just, again, so we constructed this such an algebra, cyst algebra in the algebra of bounded operators in loose space, and the map which goes to the space of continuous function on the continuous functions on the cosphere bundle, such that this holds. And really, this is another construction of this closure, but we don't appeal to this local representation to Fourier transform. And the idea is to use so-called Riesz transform, and I will talk about this later when I will talk about contact manifold and how we do this. So let's go. And another subject set, so this is Kohn-Grace theorem, and initially it was proved by Alan Kohn, and the observation was that if we take, so started with so-called X-mere trace, which is an example of singular trace on the algebra of bounded operators. And so we should consider, so we have d-dimensional manifold, and we can consider just a pseudo-differential operator of order minus d, and then it turns out that the X-mere trace of this operator exists and equals to another quantity, which is also just very famous, that which is so-called Baditsky non-commutative residue. And here is the definition of this. So it is completely given by in terms of symbols. And what is remarkable here that these both functionals are traces, which means that the trace of AB equals trace of BA. And they are different, so they don't, unlike, we know there exists a usual trace, and these traces have very nice properties, especially so so-called semi-finite normal trace. So these are so-called singular traces. They don't have such nice properties, but anyway they exist. And one can show that this is the only trace on the algebra of pseudo-differential operators. It goes back to Adler and Manian results for algebraic results for pseudo-differential operators, or for that, or in dimension one. Okay, and this is a little bit about singular traces. So to talk about singular traces, we just say, okay, we consider compact operators. Then we know that these operators always have so-called singular or characteristic values. So these are eigenvalues of absolute value of A counted with multiplicities. Then we can define so-called Wittgenstein class L1 infinity. This is the definition of this. And so in general definition, this is so the trace on this space, this is so given by this property phi of AB equals phi of BA. And one of the examples of this trace is, so this is X-mere trace, which was suggested by Jacques Dixmier in 1966. And which is given by this formula. So we have, you see, we have singular values of operator. By definition, we know that on this space, this sequence is bounded. And we can apply, and now we apply what is called Banach limit, or more, so some limiting procedure. We just fix on the space of bounded sequences. And for any limiting procedure, we can define such a trace. And it turns out, if we go back, it turns out that if we take any pseudo-differential of order minus d, then this trace exists. It is independent of omega and can be computed in these terms. In particular, this quantity is independent of the trace of Kordyukov. But we can also consider another single traces, and so also assuming that these traces are continuous, so continuity with respect to this quasi-norm, and also some normalization procedure, some normalization condition we have. So just if we take diagonal operator with this diagonal entries, we should have one. And then we can claim that, again, this is due to, so we can claim, actually, we can claim the same statement, but for, instead of trace, we can take any phi. And which is already not due to Kohn, and it has long history. Okay, and one of the examples of this, so instead of any pseudo-differential operator of order minus d, we can fix the Riemannian metric, take Laplace-Beltrami operator, and if you consider any operator for the zero, and multiply this operator by the appropriate power of this Laplacian. Namely, again, we want to have the operator minus d, so d minus d1/2. Then it turns out that this quantity can be computed in terms of the principal symbol of this operator d. And what we did, so we proved the same statement here, but we have really three differences. First, we consider any continuous normalized trace, phi. This is, as I said, this goes through. So this might quadrants make an essential role in extending this from any Dixmuir trace to the Dixmuir trace to these normalized traces. Then we take any operator, not only pseudodifferential operator, but also operator from the sister algebra of from the closure of pseudodifferential operators. And then it's really more convenient to write this. I am writing it for the future. So instead of integrating with respect to the cos-sphere bundle, we integrate to the potential bundle, but we put some Gaussian exponents there. So it's clear that if we integrate Gaussian exponent along the fiber, we really get what is dV is kind of Riemannian volume. But it's really consistent with the fact that we consider it's more convenient to consider not the cos-sphere bundle as a set of unit covectors, but as a quotient with respect to this multiplicative action by both reals. And this is a sort of cutoff function of the fibers, which is quite usual when we have proper actions of non-compactly. And so it was called following. So we call this canonical way. This move. And why Korn was interested in this, one of motivation was that actually if we take just not a pseudo-differential operator, but just multiplication operator by a function, what we get on the right, we get an integral of the function with respect to the Riemannian volume. So this is a kind of one of motivating examples in non-commutative geometry. We want to know how we can formulate Riemannian volume in terms of spectral geometry of the Laplacian. What we do? We take the Laplacian, we take this operator, we take Dixmuir trace, and what we get on the right, we get purely commutative quantity. So this is a way how we define the Riemannian volume in terms of spectral geometry. And so in our case we get here should be C, sorry, for any continuous function, and for any normalized trace we have this. So these are really some preliminaries about the classical case, but now let me go to hyperelliptic theory. And I will start with the local model of contact manifolds, which is Heisenberg group. So let's suppose we have a 2D plus 1 dimensional Heisenberg group. So this is the multiplication rule for this. We know that it's natural to consider this anisotropic dilation on this group. So this is far measure. And then we have the basis of left invariant differential operators. And we have such commutated relations, so this related with canonical anti-commutator relations in quantum mechanics. And then we take the standard sub-Laplacian. So we know that on Heisenberg group we can play with this is the simplest case of so-called sub-Riemannian manifold, and this is the simplest case of hyperelliptic operator, the sum of squares. And okay, and let's try to and we will play with this data first of all to construct pseudodifferential calculus on this Heisenberg group. And but first we have to consider operator algebras related with this. So we have representation series. So we have a left regular representation. And this is just formulated in terms of the corresponding operator algebras. So the group von Neumann algebra is just the closure of this algebra of the algebra of these operators when f is just compactly supported function. But we also have dilations. So dilations, and we should also consider operators which are dilation invariant. Dilation invariant with respect to these dilations, and the corresponding collection of dilation invariant elements will be also a von Neumann algebra, which is called homogeneous group group von Neumann algebras, and both algebras are semi-finite von Neumann algebras. And now we consider so-called Riesz transform. So actually, the blocks to construct our pseudodifferential calculus will be these operators. These are Ks. So these are zero differential operators. Zero in a sense, these are elementary zero pseudodifferential operators. So let's go to the classical case. If we just have delta just the usual Laplacian, then so they have symbols like psi I over absolute value of psi. And say in 1D this is so-called Hilbert transform, but in multidimensional case, we have such finite many operators, so such a collection of operators. And let's consider the sister algebra generated by these operators. It's easy to see that really we have these operators are dilation invariant, so they are homogeneous with respect to our dilation. And now I define the algebra of pseudodifferential operators just like as a sister algebra generated by these two sub-algebras. First, I will consider just these Riesz transforms, and I will multiply these Riesz transforms by functions which goes to the constant at infinity. So C naught means vanishes at infinity plus constant. And I take, what does it mean? What does it mean generated? So I take the sum of finite products, phi 1 of f times phi 2 of g, and then take and I just take the uniform closure. So this is really will be my algebra of zero-order pseudodifferential operators, just already taken closure. And to define the principal symbol net, what we do this. So one can see that this. So we get a symbol of this. This is a function on the Heisenberg group, which value just But so in some sense, we freeze P, we freeze point in this pi of G. So suppose I can explain, it can be also naturally explained in terms of convolution operators. So suppose, say in classical case, we have K, so we know that singular integral operators, they have, or like convolution operators, they have K of X and X minus Y, right? And what we do, we say, let us fix X. Then we have convolution of operators. So the function just X minus Y. And when we, to get the symbol, or in the classical case, we just make a Fourier transform. But here we don't have Fourier transform, but we just do at this level. And that's really the statement. So we get a surjective sub-homomorphism which goes from our algebra to the algebra of symbols. And algebra of symbols now more complicated. It's a set of functions. It's the algebra of continuous functions on the Heisenberg group with values in this sister algebra generated by all these Riesz transforms, which are left invariance operators, so they're in von Neumann algebra. And the kernel of this map is again just compact operator. So we have short exact sequence in this setting. And now we can also formulate contrast theorem on the Heisenberg group. And so we take this hyperelliptic Laplacian delta. We have any phi, and we take S, which belongs to our algebra and compactly supported to avoid problems with non-compactness of Heisenberg group. And you can compare. I take the same. You may ask why I take d plus 1 instead of d over 2. But here I play with not with 2d plus 1, which is dimension of the Heisenberg group, but with 2d plus 2, which is so-called homogeneous or Hausdorff dimension of the Heisenberg group. And what I get on the left, you can compare. So again, here instead of integration over the cotangent band, I take integration over our manifold Heisenberg group. But but here I take tau. Tau is a von Neumann trace on the algebra on the von Neumann algebra. So I have now, I remind you that I have here this non-commutative algebra in the fibers. So our symbols take values in this algebra. And there is a natural trace there, so I take trace. And another point, instead of this canonical weight, which was just this Gaussian exponent, here I have this non-commutative exponent. And but you see the formula looks quite similar if we use these notions of non-commutative analysis. And yes, I already explained here. And then if we switch to an arbitrary contact manifold, then we know, so contact manifold means that we have a smooth manifold of dimension 2d plus 1, where we have this distinguished hyperplane distribution or hyperplane bundle, such that it is locally defined by this theta, 1 on theta, and the volume form is nowhere vanishing. So, and an example is the Heisenberg group, and it turns out that this is a typical model example. So there is a Darboux theorem which says that any contact manifold looks like a Heisenberg manifold. So this goes us to the notion of Heisenberg algebras. So we can at each point we can take a chat which is diffeomorphic to the Heisenberg group. And then we know locally we have pseudodifferential operators, and we know how to construct pseudodifferential calculus once we have local pseudodifferential calculus. We have such rather standard patching procedure, and that's what we do. And we construct the algebra of this is the algebra of, again, this algebra, already this algebra of a kind of pseudo-differential operators on a contact manifold. And actually, these constructions of pseudo-differential operators has a long story, so these are just several names with several approaches. But to the classical, not without closure mainly, but so Bills-Grainer, Taylor, Epstein, Melrose, Van der Jungen, and to the principal symbol mappings of Pons, Epstein, Melrose, and Van der. And our approach different, as I explained, since we use this Riest transform. And then we can also define an analog of sub-Laplacian. Oh, sorry, and once more, so a local model was, so we have symbols which are functions in values in some non-commutative algebra, right? And so here we have this algebra of continuous section of some locally trivial bank of some Cis algebras, and I will skip this definition, of course, since I run time already, and we can also define an analog of sub-Laplacian on a contact manifold. We can also state such a Heisenberg analog of Kohn-Trace formula, but I will just show you Heisenberg analog of Kohn integration formula, which goes, and so in this case we have spectral volume. Again, we have some measure here, but it's not the Riemannian measure here, but we have such a formula for this measure in this case. So this is the domain which is useful for Riemannian measure, but we have additional term which is written here. Okay, thank you very much.
Questions? This term, something similar, comes from Dirac operators. No, here, no.
You see, and of course, as I said, yes, everything's here related with and Dirac operator and Heisenberg groups. This is always related with Meller formula. So this is again quantity which is typical. Of course, the Meller formula is behind all this, of course. Because this hit kernel for the sub-Laplacian on the Heisenberg group can be related to the hit kernel of harmonic oscillator using this Schrödinger representation of Heisenberg group. So yes.
Is it a single paper or a series of papers?
These are two papers. So first I mentioned already, but about contact it's in preparation.
So A is not the first one, the second. A.
A is just here just reminded message, yes.
No, A in 2023.
Ah, you mean AI? Yes.
the second way.
Yes, that's right. I put 2023 and 2023A, right?
So we expect B from you.
Well.
Okay, thank you very much. Об онлайн